Welcome to this video. I'm Michel Desmarais. I'll be presenting the work of my PhD student, mbouzao. We're from Polytechnic in Montreal. The work is done in collaboration with Ian Schreier from McGill University. I'll be talking about how to analyze video traces. Videos, as I don't need to emphasize that, are a major part of learning. They're a major part of MOOCs. They're about in every MOOCs. Took some statistics here from YouTube that shows that 86% of the viewers say they often use YouTube to learn new things or to solve some problems. There are a number of questions we could ask for about videos. Just like let me start from the back from the end. Engagement is a question that is often used. Can we recognize a student that is engaged? Can we recognize the students that will drop out or will succeed? Or can we recognize a high mastery or low mastery of students? Well, interaction with videos may give some answers to that. We may be interested in looking at segments of video, those that are difficult, those that we seek and go very quickly over it, so that are not very maybe too simple. Is there a learner-specific type of interaction, or do we have a style of interaction that is personal to us? Is there a style per video, like talking heads, or certain types of video would lead to certain types of interactions? So those are examples. There are plenty of others we can think of, but that's what we aim to do, provide a representation that can answer these questions. Like all logs, videos take the form of events at a given time, and then they get recorded at each event. In the case of videos, these events can be play, pause. We also have stop, seek forward, load, which means after a stop we load a video. And these events can be transformed into a sequence. That's one type of representation. So if we had a play at time 1, and then a pause at this would be time 3, time 2, then we would repeat the play until the new event comes in, at which time we have 8 of them. It gets repeated 8 times, and then a new event comes in. This is the third event, which is another play. And the sequence below is the exact opposite. We pause, play, and pause. These two sequences have the same length, but very different patterns. And one way to measure the similarity between them is the edit distance. This is the number of insertion, deletion, or changes of these would be alphabet or character between the two sequences. And in this case, of those two sequences, the distance is almost maximum. There are 12, their length is 12, and the maximum is 12, and it's 10 over 12. Another representation that is common is the Markov chain. Markov chain represents the transition between the events. So we have essentially the same sequences that we had, 2 sequences we had before, 2 seconds of play, 8 seconds of pause, 2 seconds of play, and the opposite in the bottom of the sequence. But it turns out that they have the same Markov chain representation. That is, one transition from play to pause, one transition from pause to play. So play to pause, pause to play. Pause to play, play to pause. So whereas here we have a very large difference, maximum dissimilarity or distance, here we have no difference when we take the Markov chain representation. So let's Let's look at a way to represent sequences such that we can find the patterns without going into extremes like those two representation do. So here we'll take these two examples. I'll come back to it, but those are the prototypical examples that I'll take to illustrate how the proposed measure or methodology represents the interaction and extract patterns. So the method consists in building a transition matrix. So pretty much like what we saw, the only difference is we take a minimal time step, which is the minimal time between two transitions so that we don't lose any events. And it gives us a timestamp for each transition. And we build a transition matrix. We also normalize the matrix here so that the sum equals to 1. And from this matrix representation, we can compute the distance. The distance is expressed as a Frobenius norm, which is essentially the sum of squares for each cell or each difference between the two cells and the square root of them. And we normalize by the sum of the number of transitions. And we can define this. So this is the distance or dissimilarity. We can define the similarity as 1 minus the above, the distance. Another way to measure the distance, we use the edit distance. This is the same distance that we had, the Levenshtein distance that we defined before, divided by the maximum of the number of sequences. This should be 2. Between the two, sequence 1 and sequence 2. This defines the similarity in terms of edit distance. This defines the similarity in terms of the Markov matrix, but the modified Markov matrix. And we have a rule to select the two distances, either the edit distance or the Markov matrix distance. If the two sequences are similar, then we take the Markov distance. If they are not similar, that is, their ratio of length is above 2 or below 0.5, then we essentially take the maximum. This says that we take the maximum. So that's a rule to choose between the two representations based on some thresholds. And we claim that it takes into account the time, the transition, the length of the sequences. And looking back at the prototypical examples that we had before, same length sequences, but a similar pattern in terms of transitions. How does the similarity look like? So we had essentially 16 different sequences. So 16 comparison, one sequence to the other. And we find that, of course, the diagonal is the maximum, which is 1. And we find that some of them are relatively low. This is shown by the color. If we take the edit distance. If we take the Markov chain, they're all pretty high. The lowest is about that high. So, and as expected, the proposed method considers them, all of them, fairly similar. So it essentially considers them closer to the Markov chain representation because we consider these as very much the same patterns, though not entirely similar. When we look at different length, so sequence 4 is very long length, sequence 1 is very short. Well, in this case, as expected, the edit distance considers the difference between 1 and 4 very large. They have low similarity. Whereas the Markov chain considers they have a very high similarity because they're all transitioning from play to pause all the time. The proposed method is kind of in between the two. Let's look now at that concludes the sort of face value analysis, where it shows that it behaves as we expect. How about to answer the questions that we need to be able to recognize more complex pattern, and we define complex patterns by a ground truth. That is, we hypothesize that students have a way of interacting with videos, and videos also have a way of interacting with them. They have a signature, in other words. Students have a signature interaction, videos have a signature interactions. And we will try to recognize who is interacting and which video we're interacting with, two different tasks. To do this, we'll use three different classifiers. They're shown here. So the SVM classifier. I'll get back to this slide, but I just want to show the different classifiers. The gradient boosting and the KNN classifier. So we use three classifiers and feed it with the we call it the edit sequence. That is essentially the sequence that we had before in terms of colors. We feed it the Markov chain. That is the Markov chain original representation. So we have a matrix, transform it to a vector, and feed it to a classifier. And the same process for the TMED matrix, which is also fed as a vector. We train these classifiers over with a 20-fold cross-validation approach. And we have two tasks. One is recognize one of five students or one of 12 students. And we have three measures: accuracy or balanced accuracy, and F1. And we can see that for the SVM and the KNN, the representation by TMED is better for the classification task. One exception for the JBM method. Of course, when we have fewer students, the scores are higher than when we have more students to recognize. Now, for recognizing the video, we do a similar task, but instead of recognizing who's interacting, we try to guess which video the person is interacting with. 9 videos with the number of records, 45 and 108. Again, the best performer is the TMED method. So this is telling us that the method is seems to be behaving as expected, is more powerful, is a more powerful representation to for the classification task, to recognize the signature behind either a student or a specific video. The next steps will be to go and answer the questions. Can we recognize engagement? Can we recognize low and high performing students from their interaction with video? So I thank you for your attention, and I look forward for the questions in the question period.